Opening. Tonight, we are going to follow a single question as it travels into an artificial intelligence system and returns as an answer. The journey begins with something almost too small to notice. A finger presses the enter key. A button changes color. A line of text leaves the screen. Then, after a short pause, words begin to appear in reply. From the outside, the exchange feels immediate. You ask and the machine answers. The empty space between those two events may last less than a second. Yet inside that second, the question changes form many times. It becomes a network message, then a protected stream of data, then a sequence of tokens, then a collection of numbers. Those numbers move through layers of mathematical operations running on specialized hardware. A field of possible next tokens is produced. One token is selected. Then the process repeats. The answer does not usually arrive all at once. It is assembled piece by piece, while the earlier pieces are kept in memory and the later pieces remain uncertain. The sentence that seems complete to us did not exist as a finished sentence at the beginning. It emerged one small decision at a time. We will follow this process slowly. We will not assume that every company uses the same servers, the same network, or the same model. Those details vary, and many are private. Instead, we will build a careful map of a representative modern language model pipeline. We will separate the parts that are widely documented from the parts that depend on a particular provider. There is no need to remember every technical term. You do not need to calculate a matrix or picture a circuit in exact detail. The important part is the shape of the journey. A human sentence crosses a network. It is divided into symbols. The symbols are placed into a mathematical space. The system compares each part of the prompt with other parts. Hardware moves enormous quantities of numbers through memory. A probability distribution forms. One possibility becomes visible text, then another. So settle into whatever position feels comfortable. Let the room become quieter. Imagine one small amber signal resting beside the enter key. In a moment, we will send it into the hidden machinery behind an AI response. Context will follow at a distance, watching the signal change shape without losing the question it carries. Chapter 1. The quiet moment before enter. Before the prompt begins its journey, it exists in the most familiar form it will ever have. It is a sentence on your screen. Perhaps the sentence asks for an explanation. Perhaps it requests a plan, a poem, a piece of code, or a comparison between two ideas. At this stage, the words still belong entirely to the interface. They may be stored in the memory of a browser or an application. They can be edited, deleted, copied, or rearranged. The model has not seen them. This distinction is simple but useful. Typing into a text box is not the same as sending a prompt. Until the request leaves the interface, the distant system has nothing new to process. While you type, the device performs many quiet tasks. It turns physical key presses into character codes. It places those characters in memory. It draws letter shapes on the display. It may check spelling, resize the input field, or save a temporary draft. None of this requires artificial intelligence in the large model sense. It is ordinary software responding to ordinary events. Then you press enter. The interface collects more than the visible sentence. A practical request often contains several layers. There may be system instructions that define the behavior of the assistant. There may be earlier messages from the conversation. There may be settings, identifiers, selected tools, attached files, or information about the desired output format. Some systems add safety-related context or route the request according to product features. The exact package is implementation dependent. Still, the general idea is stable. The message the model eventually receives may be larger than the single sentence you can see. Imagine placing a handwritten question into an envelope. The question is the most important object inside, but the envelope also carries an address, a return route, and instructions for handling the delivery. A digital request has a similar relationship between content and structure. The visible prompt is carried inside a larger protocol. The application now converts that structure into bytes. Bytes are small numerical units used to represent information. The familiar letters disappear behind a different notation. A capital letter, a space, a punctuation mark, and a character from another writing system can all be represented as patterns of bits. This does not yet mean that the language model is thinking in bytes. It only means that computers need a precise way to store and transmit the text. The application also needs to know where the request should go. Human users prefer names, while networks move information between addresses. A service name may need to be resolved to a reachable destination. Connections may already exist and be reused, or a new connection may need to be created. A content delivery edge, gateway, load balancer, or regional service may receive the request before it reaches any machine responsible for model inference. There is rarely one direct wire from your keyboard to one waiting artificial mind. The path is closer to a chain of doors. The first door belongs to the application. The second belongs to the network. Later doors may belong to authentication, rate limits, policy checks, routing, queues, and model servers. Some doors are passed so quickly that they feel like one event. Others may add a visible pause. At this point, it is helpful to remove one misleading picture. The AI is not necessarily sitting idle inside one particular computer, waiting only for you. Production systems serve many people. Requests arrive continuously. Hardware is shared. Work is scheduled. Models may be copied across many machines or divided across several devices. Your prompt, therefore, begins as a new task, entering a much larger flow. The amber signal leaves the text box. Context turns toward it. For a fraction of a second, the question is still close enough to recognize as language. Then the interface wraps it in structure, and the network journey begins. Chapter 2. The prompt crosses the network. The internet is often described as a cloud, but a prompt does not drift through vapor. It travels through physical equipment. Signals move through copper traces inside a device. Radio waves may carry them to a wireless access point. Light may carry them through fiber. Routers examine addresses and forward packets along available paths. At each stage, the request is represented by electrical, radio, or optical changes moving through real material. The path may be short in distance or surprisingly long. A user can be close to a regional gateway while the selected model capacity is elsewhere. Providers design their systems to reduce delay, balance demand, and respect operational boundaries, but the details vary. Modern web communication also protects data in transit. A secure connection uses a cryptographic protocol such as transport layer security. The purpose is not to make the network disappear. It is to make intercepted traffic difficult to read or alter without detection. During connection establishment, the client and server agree on cryptographic material. They authenticate the service through certificates and derive keys for protecting later application data. Once protection is active, the prompt is not supposed to cross the public network as an open sentence that every intermediate router can casually read. Encryption in transit has a precise boundary. It protects the journey between endpoints. It does not, by itself, answer what an application does with the prompt after receiving it. Storage, retention, logging, and training policies are separate questions. They belong to the service and its published terms, not to the transport encryption alone. The request may travel using HTTP over a modern transport. One documented option is HTTP3, which uses QUIC and relies on TLS 1.3 or greater during its handshake. Other services may use HTTP2 or another design. The protocol can change without changing the conceptual story. Structured data is protected, transmitted, acknowledged, and delivered to a server-side entry point. Packets are smaller than the complete meaning of the question. A network does not need to understand the request as a request about astronomy, software, or dinner. It moves addressed data. Meaning returns later, after the receiving software reassembles and interprets the message. At the provider's edge, the request may pass through several practical checks. Is the authentication valid? Is the account permitted to use the selected service? Has a rate limit been exceeded? Is the request too large? Which region, model deployment, or capacity pool should receive it? This routing work is not the language model's answer. It is the surrounding system making sure that the answer can be computed. Imagine a great observatory with many telescopes and only a limited number of operators. Questions arrive like observation requests. A coordinator does not solve the scientific problem. It decides which instrument is appropriate when it is available and how the result will return to the correct observer. Large AI services require similar coordination. Some requests are short. Some have long conversation histories. Some ask for a few words. Others ask for thousands. Some may be compatible with the same hardware batch. Others may need different models, modalities, or tools. The request can therefore spend a small amount of time in a queue. Queuing is not always a sign of failure. It is a method for organizing shared resources. A system may wait briefly so that several compatible pieces of work can be processed together. The right balance depends on whether the service is optimizing for the lowest possible delay, the greatest total throughput, or some mixture of both. Serving frameworks document techniques such as in-flight batching. Instead of waiting for a fixed group of requests to begin and end together, the scheduler can add and remove work as different requests progress. One response may be on its 20th generated token, while another request has just completed preprocessing. The hardware remains busy, while each user receives an independent stream. This is one of the first places where the simple conversation metaphor breaks. Several conversations can share the same moment of computation without mixing their content. The scheduler keeps their states separate while arranging their numerical work efficiently. Eventually, your request reaches preprocessing. The protected message has arrived. The server reconstructs the application data and extracts the text and instructions that will become model input. The amber signal has crossed the network. It has passed through routes and gates, but it is still not yet in the form a language model uses. It must now be divided into a new alphabet. Chapter 3. Words become tokens. People read sentences as words, phrases, and meanings. A language model begins with a more mechanical problem. It needs a finite set of symbols that can be assigned numbers. Those symbols are called tokens. A token is not always a word. It may be a complete common word, part of a longer word, punctuation, whitespace, a fragment of code, or a sequence of bytes. The exact division depends on the tokenizer. This means that the sentence you typed has no universal token count. Change the tokenizer, and the boundaries can change. A familiar English word may be one token in one vocabulary and several tokens in another. A rare name may split into smaller pieces. Languages and writing systems can be segmented with different efficiency. OpenAI's published TikToken library provides a clear example based on byte pair encoding. Its documentation describes language model input as a sequence of numbers and explains several useful properties. The encoding is reversible. It can represent arbitrary text. It compresses common patterns. It can preserve common subword pieces that appear across many words. Consider the ending ing. It appears in walking, reading, thinking, and many other English words. A tokenizer may learn that this recurring sequence is useful as a unit. The model can then encounter the same token in many contexts. Tokenization is not linguistic truth. It is an engineering compromise between a vocabulary that is too small and one that is too large. If every token represented only one byte or character, sequences would become long. The model would need more steps to represent ordinary language. If every possible word had its own token, the vocabulary would become enormous and still fail on new names, spelling variations, and arbitrary strings. Subword and byte-based approaches create a middle path. Common patterns can be compact, while unfamiliar text can still be represented through smaller pieces. The tokenizer scans the prompt and returns token identifiers. A sentence that looked continuous becomes a list of integers. The integers do not contain meaning by themselves. Token number 42 is not inherently more thoughtful than token number 41. The number is an index into a vocabulary agreed upon during the model's design and training. Special tokens may also mark boundaries or roles. A system can use reserved symbols to distinguish instructions, user messages, assistant messages, tool results, or the end of a sequence. These symbols are part of the surrounding format. They help the model receive a structured conversation rather than an undifferentiated wall of text. At this stage, the conversation history matters. If earlier messages are included, they are tokenized too. A short new question can therefore produce a large input sequence when it follows a long discussion. The maximum amount of usable input and output is often described as a context window. The precise limit depends on the model and product. The important idea is that the active sequence occupies finite computational and memory resources. Longer context is not free. More tokens require more representation, more memory, and usually more work. Ordinary attention compares positions across a sequence, so the cost can grow quickly as the sequence becomes longer. Modern systems use optimized kernels, sparse patterns, caching, and other techniques to make long contexts more practical, but the underlying resource problem remains. Tokenization also explains a few experiences that otherwise seem mysterious. A model may handle a common phrase smoothly yet struggle with an unusual string of characters. Counting letters can be awkward because the model sees token pieces, not a clean row of individual letters. Two prompts that look similar to a person may produce different token sequences. None of this means that the model is limited to manipulating visible fragments without broader patterns. Later layers learn relationships across tokens. Still, the initial segmentation shapes the raw material they receive. Imagine our amber signal entering a circular chamber. The sentence passes through the center. On the other side, it emerges as a train of small tiles. Some tiles hold whole words, some hold endings, some hold spaces and punctuation. Each tile carries a number. Context follows the train, and projects a simple reminder into the dark. The model does not receive your sentence as a sentence. It receives a sequence of token identifiers. The token train is now ready for the next transformation. Numbers that merely name symbols must become numbers that can participate in learned relationships. Chapter 4. Tokens enter a mathematical space. A token identifier is an address. The model needs a richer representation before it can calculate how tokens relate to one another. The first major step is an embedding. An embedding turns each token identifier into a vector, which is an ordered list of numbers. Instead of one integer saying which token this is, the model receives many values that place the token inside a high-dimensional learned space. The dimensions do not come with simple labels. There is usually no single coordinate named kindness, astronomy, or grammar. Meaning is distributed. Patterns emerge across many dimensions and many layers. During training, the model's parameters were adjusted repeatedly so that these representations became useful for predicting text. Tokens used in related contexts can develop related patterns, but the geometry is not a perfect dictionary of human concepts. It is a learned computational structure. The prompt has now become a grid of numbers. One direction corresponds to positions in the token sequence. Another corresponds to dimensions in the model's internal representation. But a new problem appears. If the same token occurs twice, the token embedding alone does not say which occurrence came first. Order matters in language. The machine helps the person is different from the person helps the machine. The words are similar, but their positions change the relationship. Transformer systems therefore add position information. The original transformer paper used positional encodings. Modern systems may use learned positions, rotary position embeddings, or other methods. The implementation can vary, but the purpose is similar. Give the network information about where each token belongs in the sequence. Token identity and position are combined into the state that enters the first transformer layer. It is tempting to imagine this state as a row of tiny definitions. That picture is too static. The initial vectors are only a starting point. As the prompt passes through layers, each position is updated according to learned transformations and relationships with other positions. The word bank can refer to money or the side of a river. Its initial token representation does not need to settle the question alone. Nearby and distant context can gradually push the active representation toward the relevant use. If the prompt says, "We sat on the bank and watched the water," relationships with sat and water become important. If it says, "The bank approved the loan," approved and loan guide the representation differently. This is one reason context matters so much. A token is not processed as an isolated label. Its working representation changes as the network integrates information from the sequence. Instructions also become part of this context. The difference between "translate this sentence," "criticize this sentence," and "continue this sentence" is not a physical switch on the outside of the model. The instruction is represented in the same broad numerical world as the text it governs. The trained network has learned patterns that connect these instruction forms with different continuations. No model weight needs to be rewritten for each ordinary prompt. The prompt changes the temporary activations moving through the model, not usually the long-term parameters learned during training. This separates training from inference. Training is the long process in which examples influence the model's parameters. Inference is the process of using those parameters on a new input. A conversation can feel like the system is learning because later messages affect later answers. Often, however, the system is using the earlier messages as context rather than changing its trained weights. The distinction is important. Temporary context can disappear when the conversation ends or when the system no longer includes it. Persistent memory, if a product offers it, is an additional mechanism with its own design and policy. Inside the observatory, the token tiles dissolve into constellations. Each tile becomes a point surrounded by many faint coordinates. Positional arcs connect the points in order. The sentence is no longer visible, yet its structure has not been lost. It has been translated into a form the network can transform. The amber signal rests at the first layer. Ahead lies the mechanism that gave the transformer its name and much of its power: attention. Chapter 5. Attention moves through the prompt. The word attention carries a human meaning. We choose to attend to a sound, a face, or a thought. Transformer attention is a mathematical operation. The metaphor is useful, but it should not be mistaken for an inner observer. The original transformer paper described attention using queries, keys, and values. These names sound like objects from a search system. At each position, the model creates a query representation. Other positions provide key representations. A comparison between query and key produces a measure of relevance. The resulting weights are used to combine value representations. In simpler language, each token position asks a learned question of the surrounding context. Which other positions should influence my next update, and by how much? The question is not written in English. It is expressed through vectors and dot products. The relationships were shaped during training. Suppose the prompt contains the sentence, "The telescope could not focus because it was still moving." The token corresponding to it may need information from telescope. Attention provides a path through which one position can draw from another. In a different sentence, the same pronoun may connect elsewhere. One attention pattern is not enough for every relationship. Transformers commonly use multiple attention heads. Different heads can learn different ways of combining information. One may become useful for nearby syntax. Another may track a long-range reference. Another may respond to formatting, position, or a pattern that has no simple human name. It is tempting to assign a clean job to every head. Research sometimes finds interpretable behavior, but a production model is not a cabinet of neatly labeled rules. Functions overlap. Representations are distributed. The important fact is that multiple learned relationship patterns can operate in parallel. The attention scores are normalized so that they become weights. The values from different positions are mixed accordingly. The result is added back into the ongoing representation through a residual path. Residual connections allow information to continue through deep networks without being replaced completely at each step. Layer normalization and related techniques help keep activations in workable ranges. A feed-forward network then transforms each position further. Attention mixes information across positions. The feed-forward part performs a learned transformation at each position. Together, these components form a transformer block. Then the block repeats. The prompt passes through layer after layer. Early layers begin with token and position information. Later layers operate on representations that already contain context gathered below. No single layer needs to solve the whole request. The model's computation is distributed across depth. Patterns can be assembled gradually. If the prompt asks for a comparison, the network must represent the things being compared, the requested criteria, the desired tone, and the surrounding instructions. If it contains examples, those examples can shape the continuation. If it asks for code, formatting patterns and language conventions become relevant. The model is still performing numerical transformations. Yet the transformations were trained on language, so they can reproduce a remarkable range of linguistic structures. Attention also creates a resource challenge. In ordinary self-attention, positions are compared across a sequence. As sequences grow, the number of possible comparisons grows quickly. Long prompts therefore increase more than the amount of text stored. They can increase the work and memory needed to relate that text. Efficient implementations spend enormous effort not only on arithmetic, but on moving data. Flash attention provides a clear example. Its authors described attention as an input and output problem between levels of GPU memory. High bandwidth memory can hold large tensors, while smaller on-chip memory is much faster to access. A naive algorithm may repeatedly move large intermediate results back and forth. Flash attention reorganizes exact attention into tiles. It performs useful work in smaller blocks and reduces transfers between memory levels. The mathematical result can remain exact while the path taken by the hardware becomes more efficient. This teaches a broader lesson about AI systems. A faster algorithm does not always come from doing less mathematics. Sometimes it comes from moving the same mathematics through the machine more intelligently. The layer's output is a tensor, a structured block of numbers. Hardware kernels multiply, add, normalize, and transform these tensors. Thousands of small operations are organized into larger parallel workloads. The model does not pause after each layer to translate its state back into words. The human-readable sentence remains absent. Only the numerical representation moves forward. At the top of the model, the final active representation at the current generation position is transformed into scores over the token vocabulary. These scores are often called logits. For every possible next token, the model produces a value. The values do not yet form a probability distribution, but they can be converted into one. Common continuations may receive high scores. Implausible continuations may receive low scores. The distribution reflects both the prompt and every output token generated so far. We have reached the place where an answer could begin. But before one token becomes visible, it is worth looking beneath the mathematics at the hardware carrying it. The transformer may be described in equations, yet the equations must occupy memory, consume energy, and share time with other requests. Context moves past the attention lattice. Thousands of cyan connections brighten and fade. One amber line survives to the far side, carrying the prompt's active state toward the machine room. Chapter 6: The Machine Room of GPUs and Memory. A trained language model contains parameters. These are numerical values adjusted during training and then loaded for inference. Large models can require more memory than one device provides. A serving system may place the model on one accelerator, divide it across several accelerators, keep multiple copies for capacity, or route work through specialized components. Some architectures use mixture of experts layers, where only selected parameter groups are active for a particular token. Others use dense layers, where the full relevant block participates. The exact arrangement is provider-specific. The general requirement is not. Parameters and activations must be available to hardware quickly enough to produce a useful response. Graphics processing units became important to modern AI because they are designed for highly parallel numerical work. A language model repeatedly performs large matrix operations. Many products must be multiplied and accumulated. Specialized accelerators can perform these operations across large arrays of computing units. The word graphics remains in the name, but the hardware is not drawing a picture of the answer. It is applying numerical kernels to tensors. Arithmetic is only part of the challenge. Data must move from storage into memory, from memory into processing units, and between devices when the model is distributed. Memory bandwidth often matters as much as raw calculation. A processor can perform many operations per second, but only if it receives the required numbers in time. If it waits for data, theoretical computing power remains unused. This is why modern inference software includes fused operations, quantization, paged memory, and carefully designed kernels. Fusion combines stages so that intermediate results do not need to travel through memory as often. Quantization represents some values with fewer bits, reducing memory use and movement, though the acceptable trade-off depends on the model and method. Paged memory organizes temporary state in blocks that can be allocated more flexibly. The prompt has two broad phases of model computation. First comes processing the existing context. The model passes the input tokens through the network so that it can build the state needed to predict the first output token. This phase is sometimes called prefill. Then comes decoding. During decoding, the system generates new tokens one at a time. Each new token extends the sequence. Without optimization, the model might repeatedly recompute information from every earlier token. That would waste work. Transformer inference systems therefore use a key-value cache, usually shortened to KV cache. At each transformer layer, earlier tokens produced key and value tensors for attention. The cache stores these tensors. When a new token is generated, the system calculates new state for that token and attends to the stored earlier state. The cache grows as the sequence grows. This gives the conversation a physical footprint in device memory. A longer prompt and a longer answer require more cached state. The footprint depends on the architecture, number of layers, attention design, precision, and serving software. The model's trained parameters are broadly shared across requests. The KV cache is temporary state associated with a particular active sequence. Imagine a quiet archive running alongside the computation. Each time the model adds a token, every layer places a small record into the archive. When the next token is considered, the model can consult the accumulated records rather than rebuilding the entire past. The archive can become large. It can also be awkward to manage because requests begin and end at different times. One user may send a long document. Another may ask a short question. One answer may finish quickly while another continues. Traditional contiguous memory allocation can leave gaps. The paged attention paper borrowed an idea from virtual memory. Instead of requiring one uninterrupted region for each request's growing cache, the system can manage state in blocks. This reduces fragmentation and enables more flexible sharing in supported cases. Production frameworks also use in-flight batching. A GPU can process token steps for several requests together. As one request ends, another can join. The group is not fixed for the entire lifetime of every response. This means your token may be calculated beside tokens belonging to other users without becoming part of their conversations. The serving layer tracks which temporary state belongs to which request. The arrangement resembles a railway station more than a private road. Trains arrive at different times. Cars are organized into available paths. Signals prevent routes from crossing incorrectly. The station becomes efficient by sharing infrastructure, not by confusing destinations. When a model is divided across devices, one token step may involve communication between accelerators. Different forms of parallelism divide parameters, layers, or experts. The system must coordinate these pieces quickly enough that the user sees a continuous response. The time before the first visible token is influenced by several factors: network delay, queuing, preprocessing, the length of the prompt, model size, hardware availability, and the work needed for prefill. After the first token, another measurement becomes noticeable: the rate at which new tokens appear. These two delays are different. A system can have a longer pause before beginning and then generate rapidly. Another can start quickly but stream more slowly. The user sees only a blinking cursor. Behind it, the machine room is balancing latency, throughput, memory, and power. Our amber signal passes through rows of numerical machinery. It does not move as a single file. Its representation is distributed across tensors and devices. Yet the serving system keeps enough order to return one coherent stream to the correct conversation. At last, the top layer has produced logits for the next token. The machine has not written a complete answer. It has produced a landscape of possibilities. Chapter 7. One token is chosen, then another. At the end of a generation step, the model has a score for every token in its vocabulary. The scores can be transformed into probabilities using a function called softmax. Tokens with higher logits receive more probability. Tokens with much lower logits receive less. This probability distribution is conditional. It depends on the prompt and on every output token already generated. Suppose the visible answer begins. The main reason is the distribution for the next token will differ from the distribution after. Once upon a time, change one earlier token and many later probabilities can shift. Generation therefore forms a chain. Each selected token becomes part of the context for the next selection. The simplest strategy would always choose the highest probability token. This is often called greedy decoding. It can be useful, but it may also produce repetitive or overly predictable text. Other strategies sample from a controlled set of possibilities. Temperature changes the shape of the distribution. A lower temperature generally makes high probability tokens more dominant. A higher temperature spreads probability more broadly and increases variation. Nucleus sampling, often represented by top P, limits consideration to the smallest group of tokens whose cumulative probability reaches a chosen threshold. The candidate group can change at every step. When the model is confident, the group may be small. When the distribution is broad, more tokens may remain. Products do not always expose these controls, and newer reasoning systems may place additional processes around basic decoding. Still, token selection remains a useful foundation for understanding text generation. Calling the process random is incomplete. The model's distribution is highly structured by the prompt, its training, its architecture, and the generated context. Randomness, when used, operates within that structured distribution. It does not choose equally among every word. Imagine a dark landscape with thousands of paths. Most are almost invisible. A few are brightly lit. Sampling may introduce variation among the plausible paths, but the terrain itself was shaped by the model. Once a token is selected, it is appended to the sequence. The tokenizer can decode its identifier back into bytes and text. The system may not send it to the user immediately. It may buffer small pieces, check stop conditions, apply formatting, or wait until bytes form valid displayable characters. Then the new token returns through the transformer. Its key and value state is added to the cache at every relevant layer. Attention uses the earlier cached state. New logits appear. Another token is selected. This loop continues. Represent the newest token. Update it through transformer layers. Produce logits. Form a distribution. Select a token. Append it to the sequence. The answer grows from left to right. The model is not necessarily holding a complete hidden paragraph and revealing it slowly. In a basic autoregressive pipeline, later wording does not yet exist as a final sequence. The system may represent plans or latent structure, and modern systems can perform internal reasoning or use more complex generation strategies, but visible text is still committed incrementally. This creates both power and limitation. The model can adapt its continuation to everything already written. It can preserve style, follow a list, close a quotation, or continue a line of code. But an early choice also changes the future path. A phrase can lead naturally into one explanation and make another less likely. The system may need to correct itself later using the only tool visible in the text: more text. This helps explain why two responses to the same prompt can differ. If selection is not fully deterministic, an early alternative token can send the continuation down a different branch. Even with deterministic settings, changes in model version, system instructions, tools, routing, or numerical execution can produce differences. Stop conditions eventually end the loop. The model may generate a special end token. The service may reach an output limit. A configured stop sequence may appear. A tool call may transfer control to another system. A policy layer may interrupt or transform the response. Before the end arrives, the interface can begin displaying partial output. Streaming makes a distant computation feel conversational. The server sends events as content becomes available. The client receives fragments and adds them to the screen. The cursor advances. The words you read may therefore be only a short distance behind the model's current generation state. The amber signal is no longer one signal. It has become a chain of small lights, each one influencing the next. Context watches the chain extend across the observatory, token by token, until the final light settles into place. Chapter 8: The answer returns. The generated tokens must travel back through the surrounding system. The inference server associates them with the correct request. Post-processing converts token identifiers into text. Structured outputs may be validated. Tool calls may be represented in a machine-readable format rather than ordinary prose. Usage counts, timing information, or completion status may be added to the response. Safety systems can also exist before, during, or after model generation. Their design differs across providers and products. Some checks may influence routing or instructions. Others may evaluate input or output. The important boundary is that the language model is usually part of a larger application, not the entire application. The response is protected for the network journey back. It passes through service infrastructure, gateways, and routes. Streaming events arrive at the client. The interface decodes the data and draws letters on the screen. At this final stage, the answer returns to the form in which our journey began, human-readable text. The transformation is remarkable because the beginning and end look so simple. At the beginning, a person sees a sentence. At the end, a person sees another sentence. Between them lies a system that never needed to preserve the sentence in one continuous human-readable form. The request became bytes, tokens, vectors, activations, cache entries, logits, probabilities, and tokens again. This also reveals why the phrase "the AI answered" can be both useful and misleading. It is useful because the entire system behaves like one conversational agent. The interface presents one identity. The response is coherent. The user does not need to manage tokenizers, schedulers, or GPU kernels. It is misleading if it suggests one small mind received a sentence, silently understood it as a person would, and then dictated a finished reply. The observable behavior emerges from many layers: product instructions, network protocols, preprocessing, a trained model, serving software, hardware, selection rules, and client rendering. We should also distinguish what the prompt changes. During ordinary inference, the prompt changes temporary state. It influences activations and cached representations. It does not normally rewrite the trained parameters while you wait. A service may store conversation data, provide a memory feature, collect feedback, or later use approved data in another process. Those possibilities depend on the product and policy. They are not the same as the model instantly learning a new fact into its weights from every conversation. When the active request ends, temporary resources can be released. Cache blocks can return to the serving pool. The next request may use the same hardware with a different state. The model parameters remain ready for more prompts. The answer itself may continue to exist in conversation history or product storage, depending on the service. Again, transport encryption does not decide retention. Users must look to the relevant settings and policy. What then can we honestly say happened after you pressed enter? We can say that an application packaged the prompt into a request. We can say that a network carried protected data to a service. We can say that preprocessing converted text into token identifiers. We can say that learned representations and positions entered a transformer-like computation in many modern language model systems. We can say that numerical operations moved through hardware and memory. We can say that temporary key-value state can make autoregressive decoding more efficient. We can say that the system produced scores for possible next tokens and selected tokens sequentially. We can say that decoded text returned through a streamed or completed response. We cannot assume that every provider uses the same number of layers, the same tokenizer, the same accelerator, the same batching strategy, the same safety system, or the same data policy. The map is real, but it is a map of a family of systems. Future AI products may make the journey more complicated. A request can already be routed through retrieval systems, external tools, search, code execution, image models, or several cooperating model calls. A system may plan before producing visible text. It may verify an answer, call another service, or revise an internal draft. Even then, the basic lesson remains. An AI response is not one event. It is a coordinated sequence of transformations. The apparent simplicity of the conversation is an achievement of the entire stack. Networks hide distance. Tokenizers hide representation. Serving systems hide shared hardware. The interface hides streaming protocols. The language model hides an enormous field of numerical operations behind ordinary words. The better these layers work together, the less the user notices them. Closing. Our amber signal has completed its journey. It began beside a quiet text box as a question written in human language. It crossed a protected network and entered a shared service. It was divided into tokens and placed into a mathematical space. Attention carried relationships through layers. Accelerators moved parameters and activations through memory. A probability landscape formed. One token was selected, then another, until the answer returned as light on a screen. Nothing in the journey required a complete sentence to remain visible from beginning to end. The sentence disappeared into numbers and emerged as language again. This is one of the central illusions of modern computing. The simplest interfaces often rest on the deepest machinery. The next time you press enter, you may notice the brief pause before the first word. Inside that pause is a network root, a tokenizer, a transformer, a machine room, and a field of possible continuations narrowing toward one visible answer. There is no need to follow it every time. The system was built so that you would not have to. For now, the observatory can grow quiet. Context will return the final token to its place and dim the amber signal. The model will release its temporary state. The machines will continue serving other questions at a distance. Thank you for listening. Rest well and let the next answer wait until morning.